Welcome to This Explainer. I'm your host, and today we are going to decode exactly what Cambridge examiners are looking for, transforming your average, run-of-the-mill grades into top-tier A-star marks. Now, picture this scenario for a second. You are sitting right there in the exam hall, the clock is ticking down, the pressure is on, and you flip the page to face a classic 8-mark question on comparing bitmap images and vector graphics. Specifically, it's asking you for a justification for use in a given scenario. Now, on the surface, it seems pretty simple, right? But here is where the battle for that A-star is truly fought and won. To really set the stage for you, I want you to imagine two different students. Let's call them Alex and Sam. So Alex looks at this exact question and immediately just overloads the page with raw computer science facts. Alex writes, bitmaps use pixels, vectors use math. Bitmaps get blurry, vectors do not. I mean, it is factually true, sure, but there's absolutely zero critical analysis there. Now, Sam, on the other hand, well, Sam rushes. Sam spots the word vector, completely ignores the specific command words in the prompt, and just scribbles down use a vector because it scales. Sam misses the comparative requirements entirely. And the result? Both Alex and Sam walk out of that hall thinking they absolutely nailed it, only to be totally shocked by a C grade on results day. Today, we are going to fix that. Whether you're studying syllabus 0417, 0478, 0983, 0984, 2210, or especially 9618, we are going to navigate by the stars, those key command words, and chart your course to maximum marks. Okay, let's dive straight into this insider's playbook, starting with a direct quote from a senior examiner that really raises the stakes right out of the gate. They said, the difference between a B and an A-star in computer science often comes down to how well you understand comparing bitmap images and vector graphics, justification for use. Now, you've got to ask yourself, why is this specific topic such a gatekeeper for top grades? Why do they care so much? It's because it perfectly tests your ability to bridge that gap between theoretical knowledge and practical, real-world application. Examiners actively use this topic to separate the candidates who just memorize the textbook cover to cover from the candidates who can actually think, analyze, and problem-solve like real computer scientists. When an examiner sees our buddy Alex just listing off facts about pixels and color depth, or they see Sam completely ignoring the specific scenario, say they were asked about a web designer creating a highly scalable logo versus a photographer editing a massive high-resolution landscape, they instantly know these candidates lack the deeper evaluative skills required for the top grade. They want to see you weigh file size against image quality. They want to see you weigh scalability against photorealism. Mastering this specific comparison isn't just about knowing images. It is a live demonstration of your entire analytical capability in computer science. So, to navigate this complex topic successfully and outsmart the test, we're going to follow a very logical, step-by-step roadmap today. First step, we'll hit the core principles. Second, we're going to break down the method mark strategy. Third, we'll get into mastering comparative analysis. And finally, we will expose the top 3 examiner traps. Let's get into it. All right, kicking things off with Section 1, Core Principles and the Theoretical Framework. Now, let's talk about what we mean by a theoretical architecture. It means you don't just know the basic trivia that a bitmap is made out of a grid of pixels. You actually understand the causal relationship beneath it. You understand that increasing the resolution improves the quality, sure, but it also exponentially increases storage requirements and transmission time over a network. Top candidates, the ones securing those A-stars, transfer this conceptual understanding instantly to totally unfamiliar scenarios, whether the exam asks about an MRI machine's display or a brand new smartphone game. They read the prompt and instantly assess the situation. They think, okay, does this scenario require photorealism at a fixed resolution? Yes, then we need a bitmap. Or does it require geometric precision, constant resizing, and tiny file sizes for simple shapes? Yes, then vector is the way to go. This fluid thinking is the exact difference between just reciting facts like a robot and demonstrating genuine mastery of the subject. Let's bring Alex back into the picture for a second to really illustrate this. Alex, our average candidate, looks at the prompt and basically just word vomits a mental data dump onto the page. Top-scoring candidates, however, approach this completely differently. They use proven frameworks like PEAL. You know PEAL, right? Point, evidence, explanation, link. It's an absolute game changer. For instance, if your command word is evaluate, a top candidate starts with a clear point. Vectors are superior for the corporate logo. Then they drop the evidence. Vectors store image data as mathematical equations rather than individual pixels. Next comes the explanation. This means the logo can be scaled up to fit a massive billboard without any loss of quality or pixelation. And finally, they bring it all home with a link. Therefore, for a company needing the exact same logo on a tiny business card and a huge advertisement, vector is the only justifiable choice. Do you see the difference there? Mastering frameworks like PEAL is literally how you elevate your grade. And hey, speaking of elevating your grade, Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Trust me, you don't want to miss the strategies we're dropping. Moving right along, let's look at the actual engine of your exam success in Section 2, the method mark strategy. So here's something crucial to wrap your head around. Algorithmic thinking isn't just a concept for when you're writing Python or pseudocode. It applies directly to how you structure your written theory answers, too. When the Cambridge syllabus mentions method marks, it essentially means that if you demonstrate a clear, logical, step-by-step decomposition of the problem, the examiners actually award you marks for the process itself, even if your final conclusion ends up being slightly off base. Think of it like this. You are given an input, which is a scenario about a graphic designer choosing an image format. You need to process this input systematically. You parse the input, you identify the core variables, and you process them step by step to extract the relevant data. You are basically making your invisible thinking process entirely visible on the paper for the examiner to grade. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at aceexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, now let's actually execute a live transformation using this 5-step blueprint. I want you to look at a classic past paper scenario. Justify the use of a bitmap format for a digital photograph taken by a smartphone. All right, step 1, deconstruct. Our key command word is justify, and our key subjects are bitmap and digital photograph. Step 2, extract the data. What do we know? A photograph inherently requires incredibly high detail and photorealism. Step 3, execute the analysis. Bitmaps represent images as a massive grid of pixels with specific color depths. This allows for the continuous tone images and subtle color gradients that mathematical vectors just cannot easily replicate. Step 4, verify. Did we actually explain why vectors fail and bitmaps succeed for this specific scenario? Yes, we did. Step 5, present it properly. We ensure our terminology is razor sharp. By following this exact algorithmic sequence, we've just transformed a panicked, chaotic draft into a beautifully structured, full-mark answer. Now let's see how this builds into the specific requirements for our next major topic, Section 3, Mastering Comparative Analysis. Let's do a quick interactive workshop right now. When you are justifying your use of an image format, you absolutely cannot just list features. You must actively contrast them using what examiners call comparative connectives. I'm talking about words like whereas, conversely, in contrast, or on the other hand. Okay, challenge 1. Let's do a quick mental data scan. Imagine I show you a table. File A is 15 megabytes, highly detailed, but it loses quality when zoomed in. File B is only 45 kilobytes, made of simple shapes with infinite zoom capability. What's the core trend here? Take a second. You got it. File A is our bitmap and file B is our vector. Now, challenge 2, find the flaw. Listen to this sample paragraph and tell me where Sam went wrong. Bitmaps use a lot of memory. Vectors use mathematical coordinates to draw shapes. I recommend a vector. Did you catch the flaw? The fatal flaw there is the total lack of a comparative connective linking the memory usage to the technical structure. Let's do a speed rewrite to fix it. We say, bitmaps use significant memory because data for every individual pixel must be stored, whereas vectors require much less storage because they only store mathematical instructions. Boom. That single word whereas completely fulfills the rigorous syllabus requirement for critical analysis. By systematically analyzing these trade-offs and acknowledging the limitations of both formats, your mental algorithm for answering these questions practically guarantees top marks. Look, considering multiple solutions means recognizing that both formats have their rightful place in computer science. Analyzing trade-offs is where you show off. For example, if you tried to use a vector graphic for an incredibly complex, highly detailed nature scene, the sheer processing power required for the CPU to calculate millions of complex mathematical equations in real time might actually exceed the resources needed to just display a standard bitmap. Acknowledging limitations like that shows the examiner you aren't just reciting a textbook, you understand the real-world physical boundaries of computer science. You might write something like, while vector graphics are highly scalable, their core limitation is an inability to capture the subtle, continuous color gradients of natural, real-world scenes. This is the exact level of nuance that proves you are deeply analyzing the technological realities. All right, now for the survival guide portion of our explainer. Let's get into Section 4, Top 3 Examiner Traps. These are the trapdoors you absolutely must avoid. Reading through years of principal examiner reports, we have identified exactly 3 critical mistakes, 3 specific traps that consistently cost smart students their A-star grade. Let's make sure you never fall into them. Let's break down these 3 examiner warnings quickly. Trap number 1, confusing cause and effect. Remember, the cause is that a bitmap must store binary data for every single pixel. Therefore, an increase in resolution causes the effect of a massively increased file size. Don't mix those up. Trap number 2, forgetting edge cases. If you aggressively scale a high-resolution bitmap down to a tiny thumbnail, like an edge case scenario, you often lose vital detail because pixels literally have to be discarded by the software. And trap number 3, the biggest one, ignoring the context. If the exam asks about a web graphic that needs to load instantly on a 3G connection, and you don't explicitly link the smaller vector file sizes to faster download speeds and bandwidth conservation, you fall directly into the trap. You lose those vital application marks.
And here is the examiner alert you need to sear into your brain. The absolute golden rule to take away from this explainer is to define your technical vocabulary before you start throwing it around in your application. If you are comparing the two formats, take just one sentence to define your core term. State clearly, a bitmap is composed of a matrix of individual picture elements, or pixels, where each pixel has a specific binary value. Then state, a vector graphic uses geometric primitives such as points, lines, curves, and polygons, all based on mathematical expressions. By defining these terms right out of the gate, you immediately signal to the examiner that you possess a rigorous, precise understanding of the theoretical architecture. You're setting the foundation for your PL paragraph perfectly.
So, let's bring it all together. Students who implement these specific computer science strategies, decoding the command words, utilizing the Peel framework, and managing their time effectively, see an average improvement of 2 whole grade boundaries. But that's only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every single comment. Like and share this video with a study partner. Remember, the next time you sit down in that exam hall and see a question about images, ask yourself, are you just going to recite facts like Alex, or are you going to engineer a brilliant solution like a true computer scientist? The choice and the A-star is yours. AC Exams, your Cambridge success starts here.